pocket, put it in my pocket, in my pocket, in my back pocket. Oh, oh, oh. And I put it in my pocket, put it in my pocket, in my back pocket, put it in my pocket, in my pocket, in my back pocket, and I'll read it when I'm alone. Do you like me? Circle yes or no on this piece of paper, 'cause I really, really need to know. Are you gonna be my fifth grade queen?
Are you gonna be? Are you gonna be?
Hand it back after second hour, then I will know if you're gonna be my special flower. Ooh, girl, 'cause I need to know. I will put it in my pocket, put it in my pocket, in my back pocket, put it in my pocket, in my pocket, in my back pocket. Oh, oh, oh. And I put it in my pocket, put it in my pocket, in my back pocket, put it in my pocket, in my pocket, in my back pocket, and I'll read it.
All right, good afternoon, everyone. Sorry for the delay because I was actually dealing with a technical issue between Zoom and YouTube. And for some reason, I think some update in Zoom right now giving an error like, well, your broadcast quota exceed what YouTube is allowed. So there are definitely something beyond my control that Zoom is doing right now, has some issues with YouTube, but don't worry about that. I will, well, in the meantime, we are also recording our lecture and I will upload our recorded lecture on YouTube as well. So don't worry, you can always see our recording on YouTube. So let's talk about what we are going to, so with that, right now, let's talk about where we were. So previously we were talking about, like, we are going to talk about, so in the last week we were at the session of RTL Design, and we talk about right now, well, you have the design in mind, you have the Datapath component in mind, but you know, when we design a circuit, usually we want a circuit to have as many functions as possible. So how to design a full system that contains all these features and have all the features that works together, how to have all the Datapath components working together fine in implementing the features that we want. So that's the whole purpose of a more high-level design. So it turns out that the design process of at this level, what you need is not a finite state machine, but a high-level state machine. So the high-level state machine is similar to the finite state machine in a way that we still have states. However, because we want to simplify the transition. So instead of having lots of states transition on just one bit of data, right now you could have a state machine that transition on multiple bits of data on depending on multiple control signals, not just one. So in this way, it's a simplified description of the functionality or the circuit, or say the system that you want to design. So to begin with, how to design a high-level state machine? To begin with, you always have to keep in mind, what are your inputs? What are your outputs? And what are the local register or the data storage in your design? And then clearly specify the size of bits of each of them, because later on you will need some data path components that would help you to implement this high-level state machine. And for each state, for when you are transitioning in each state, update the value of registers, update the value of outputs. And on transition, you express a condition that would cause the transition, and the arithmetic operation that that judge if the transition is going to happen or not. And then after you have this highlight state machine, the next step is always like that's converted to a circuit. So to convert a circuit, first of all, you need to create a data path, and the data path components like register, adders, comparators, multipliers, dividers, we have talked. And for the data, and then we connect the data path controller, the data path to a controller for the controller block to control or to signal those data path components, to signal those input signals of muxes to make them working, functioning correctly. And we have to clearly label all control signals that are exchanged between the data path and the controller, and then finally derive the controller's finite state machine. That's the only time you will need the finite state machine when you are designing the low-level circuit. So so right now, if we are talking about the design of the system, the first thing that you have in mind is that, okay, what's the high-level state machine? And then let's dive into the detail, thinking about what we need, and finally implement the finite state machine. Okay, so that's the design summary, and that's where we end up with. So and we talk about the soda dispenser, right? So the soda dispenser is something that in the very beginning, you put no money in there, and you go to that soda dispenser, you figure out that I need to put, say, like a $1.25. And then you gradually put your coins or your bills in there. And when the machine receives that, that's judge if you got the sufficient amount of money inside the machine to see if we can dispense the stuff we want. So the high-level idea is that, well, first of all, you need a total register to tell you what's the total amount of money that you put into the machine. And if we can if we can dispense the stuff you want. And after we initialize everything, we go into a wait state, which is waiting for the customer to put something. And there's another signal called C, which means that the customer put a coin in there. And when you put a coin in there, we will add that to your current total. So that's why we have the total plus A here. And let's judge if the coin is right now in a status that is reach our total. So if it's equivalent to our total, which means that the C lines and the total smaller than S must be both true. So in this way, we can dispense the stuff that the soda, which means that we are going to change that to 1. If not, then we keep waiting for the customer to put more money in there. So that's the basic idea of the soda dispenser. And as you can imagine, once you have this high-level state machine, you know, well, I need a total, which require you to have a register here. And because I have to do addition, so you know I need an adder here. Because I want to compare if this thing is smaller than S. So I need an 8-bit S here. And I also need an S to be another input. In the meantime, you have to output something to indicate if it's smaller than S. So that's the basic idea of the high-level state machine for the soda dispenser. So just listen to me. It's probably not giving you a feeling about how the high-level state machine would work. So let's try this question and see by how much you understand the concept of a high-level state machine at this point. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from you, the most popular answer is E and then followed by C. So can I have some of you share your thoughts with me regarding how you derive the answer? Okay, I have Sheila. What do you think?
Personally, I chose E,
Uh-huh.
and I chose E because when you're loading a value into the register, you have to keep in mind that the total might change if you're getting one or more sodas, especially with the dispensers at our campus. So that means you can add on to the total, or you can clear the total once it's done dispensing, so it's back to 0. So that means it has to be both C and D.
Okay, so the question I have, well, so according to the current design, right? So in this current design, what's changed? Well, so, okay, so this is the current design, right? So do you see anything that would make these two signals change?
Okay, well, there's the 8-bit adder, and then there's the dispense. Wait, hang on. Okay, there's an initialization, and then there's add.
Okay, so under which of the following condition does the register output total change at the rising clock age? What does that mean? You are going to change your value, right, when you are transitioned to a state, right?
Yes.
Because the high-level state machine has its transition happening on the rising edge of a clock, right?
Okay, so that would be add that.
So then what signal would, or say which of the following condition would do that? Like, is there anything here saying about a total load or total clear?
Not necessarily in the finite state machine. It seems to be.
Well, it didn't say anything. It's not necessarily. It's nothing, right? So actually, they are both wrong answer. So it means this one is also not the right answer. So in this way, what are if we have the remaining two, right? Which one would cause the output of total to change? A or S?
I would believe it to be S.
So how, well, so if you look at the right hand side, right, who is the input of total?
Wait, it would be
it
would be the adder A, right? So the answer would be A.
So it's the output of the adder, right? And the output of adder depending on what?
Depending on total or A there. Those
Right, depending on the total of A or A, right? And total is not a condition that would change externally, right? So on the hardware side, right, the only thing that would change the total on the rising clock age is actually the output of the adder, which comes from A, right? And if you go trace the high-level state machine, the only thing that would change here is this one, this assignment, right? Total plus A. So A is the right answer for this one.
Okay. Okay, I see it now.
Okay. So other people, because I think for this question, if I look at the result, only 13% of you see what's going on here. Okay, so other questions? Okay, Fox?
Well, hold on. So, okay, you said the answer is A, but
Yes.
I mean, all right, but total can change even when the value of the coin inserted doesn't change, because
Well, there's nothing here talking about the current design. There's nothing here talking about these two things, right? And the other thing is that this these two signals, they could change the total at any time, right? Even if they are connected. So it's not just rising age, right? So this is the second thing. Yeah, Nicholas, question?
Oh, I think you kind of clarified it at the end. I was kind of confused on how load and clear would be.
Well, so first of all, right, in a
SN.
current design, there's no description about the behavior of total load and total clear, right? Did you see these two things anywhere in a high-level state machine?
Right. No, I didn't.
Right. Right. And
right,
there's
but I don't know. I mean, it's the total increases when we insert a coin. So the action of inserting a coin is defined as raising the C pin and not necessarily assigning a value to A, because A is the value taken after along with C, which I mean, yes, but no.
Professor,
I just think that you can insert several quarters and argue that A isn't changing.
Well, I mean, those are the, well, this is just a simplified case, right? We are just use a simple case to explain the idea of high-level state machine, right? If you want to make this overly complicated, there's no answer here.
Oh no, I'm just saying that I don't like. Oh yeah, I don't like answer A because that condition doesn't necessarily mean that the total will change. A can be whatever it wants prior to a high input of C.
So maybe here, if we change it to C, then you will be happier, I guess.
Yes.
Okay. Yeah, but this is actually a textbook question. So that's why I don't like this textbook a lot, because sometimes they give you very confusing options.
Professor, honestly, A makes sense to me. I was just kind of confused about the load and clear. If it's not,
Yeah, but
if it's not in the
but
FSM, what role does it play?
yeah, but here's the thing, right? I agree with what Fox is talking about here, right? So the thing is that if C is not raised high, then we don't even bother doing this, right? That's what Fox is trying to say, and I kind of like agree with him at this end. Okay, so Alp, what do you think?
I was thinking same with Fox. If while answering this question, I directly associated load with C, clear with D, without paying attention to if they're mentioned in the design. But don't we increase total if we just keep A same with each rising edge?
So that's also so you are saying about for at each rising edge, right? Yeah. If A is the stand, then we will keep increasing. So that's what we are talking about here, right? So it depends on if the C is true or not, right? So if A remains the same, but if C is not changing, right? If C change back to 0, right? Then we are not adding. Okay, Fox, anything?
Yeah, I guess the one thing I did see, and I know it's kind of weird, is that because the C transitioning from weight to add, and then the total being assigned from add back to weight, this means that they're happening on 2 cycles, I guess. So yeah. So you raise C, the clock goes up, you transition to add, the clock goes down, and then it goes up again, and then we assign total. So. Right.
But
I do not like this question.
Yeah, so I think if we change this A to C, then everything makes sense.
Yes,
right?
But it will also be delayed by an entire clock cycle, the assignment.
That is true too. All right, so this question has its own flow, all right? But okay, but right now I think through this question, all of you have better understanding about high-level state machine. Is that true? Nicholas, Alp, questions still?
Oh, no. I'm just listening now. Sorry.
Okay, awesome. So, okay, Nicholas, do you still have question? Okay, if not, then we can. Okay, question. Okay, Kip. Hi, you're okay to speak.
Oh yeah, no. I'm just trying to unraise my hand.
Oh, okay, awesome. All right, so this is the concept of high-level state machine. So looks like we have a lot of misconception before we go into this question, and I think I also made a mistake by just making this slide directly from the question from the textbook, so it doesn't work very well in our case. So, but right now, let's talk about why we talk about this, right? So now we agree that we have the high-level state machine, and the high-level state machine is like that, and that part is not changing, right? So the controller's input, the external input is the C, and so this is and it means that the coin is inserted and then input from the data path, and the comparator output, which we name total minus S. So those are the inputs. And for the controller, right, this is the controller, and this is the controller. So and then we would the output we will generate is the external output, like if we are ready to dispense soda. So I guess there should be an output there, and output to the data path to load and clear the total register. So this is the design. This is the design that we end up want, right? So you want to have an input to the controller saying that I have a coin inserted. I have a D, means that the stuff is dispensed, right? And so this is the input and output that we want to present to the user. And this is the rest of the data path. And by doing this, I think the previous question was talking about, like, okay, if you look at the current design, right, what's actually changed the value of total, and you will see the input of total is coming from this one, right? So and for load or clear, it could do things at any time. So I guess that's why the original question is not favoring C and D as the answer, because for this two, they are not really necessarily happening on the rising clock age. However, for this register, right, for this, because this input is actually what you want to store in the register value, and it would definitely happen during the rising clock age. So that's why the previous question was asking like that. And I think the previous question didn't specify clearly that we are just talking about what you see in a data path component, including those signals like C and D and those output generating from here. So that's why they are talking about this, right? So this is the design, right? So we have the controller, and the controller would generate those signals to the data path elements and generate the final input and output for the user. So with this, and you can finally get the finite state machine. And the finite state machine is actually nothing too different from your high-level state machine, as you can tell from here, right? So all we need to, so this is actually the controller's finite state machine. So you still have the same amount of states, right? And then the signal that would cause you to go to add is actually to see if the C is changing or not. And if C is changing, then we have the load equal to 1, means that your total register is ready to accept a new value. But the load signal is only telling you that it's ready to accept a new signal, but not set the value of load. So that's why what really changes the value of the total is the outcome of the adder. And the finite state machine still tells if this is true, and if this is true, then we dispense the stuff, clear the register, and dispense the stuff, right? So that's the finite state machine for the controller. All right. So, and finally, right, given this, okay, so B, question? Question?
Hold up. Yeah, can you go back to the slide before real quick?
Yeah.
So like the box under the controller, that's a comparator, correct? I just wanted to double check.
Yeah. Yes,
Oh,
that's a
okay.
comparator.
Okay, yeah, that was all. Thank you.
Okay. All right. So then the final step is to implement the controller's finite state machine. So So you just implement the finite state machine as a state register and logic, which you already learned in the past. So through this example, like the soda dispenser is not perfect, but at least it gives you a very high level idea how we could design a system of circuit that works and combine all the data paths together. So so this is the example given by the textbook. It's overly simplified, but let's try another example using the stuff that you have learned before. Let's see how to build a control path of our microprocessor. So we have learned this stuff so far. We have register, we have shifter, we have adders, we have multipliers. And the processor, remember, we have only one clock generator. But as you learn, right, the timing of them are very different. So how can you control this data path components and make them work correctly? However, before we start, let's take a look about, like, if we only have one clock generator, what's the clock rate, or what's the clock cycle time we should use for the microprocessor? Up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so according to what I learned from you, about 53% of you think it's D. So can I have someone share your sharing with your sharing with your thoughts with me, with us, with all of us, not just me. Okay, so I have Fox, I have Sheila. Let's give Sheila a chance first. What do you think?
Okay, I chose D because if you remember, the clock cycle should be the highest highest period, in which in this case is 16 nanoseconds. So if you use the formula, you actually get around 62.5 megahertz, which is closest to D, which is about 50 megahertz.
Okay, so you have to, well, if we connect all of them in parallel, and the slowest component would bottleneck the processor performance, right? Which means 50 is our goal, right? So, but what if now I make some of them serial, right? So we learned those serial components, right? So what if I make some of them serial? Would that change your mind? Let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so let's take a look of your thoughts. So again, 53% of you think it's C. So can I invite some of you to share your thoughts with us? Okay, so I have Nicholas.
Okay, so I just did the 0.9 nanoseconds. I did one over the period, and then I get 1.11 gigahertz. So I
Okay.
said actually, yeah. So that's what I got.
Okay, so Fox, what do you think?
I mean, yes, do the math, but the critical path is the register and the serial 32-bit shift
Okay,
add multiplier,
so yeah,
which
so
gives us 1
I-
nanosecond critical path.
right. So another thing that you have to be careful about is that for those serial components, right, we cannot accomplish all the tasks within one cycle. So you really need is that you need something to buffer your result, and that require additional latency in the register. So the answer is indeed C. However, what I would say is like you have a register 0.1 nanosecond plus 0.9 nanosecond, 1 over that would give you 1 gigahertz. All right, Nicholas, question still?
No, that makes sense. It's because the serial needs the registers so it could buffer, right? So that's why we got to add.
Right.
Perfect.
Yeah. Okay, awesome. So right now, let's say like I have this processor, and what if and as we learned, the clock rate is like that. But what if I change the latency of some of the component? Does that change your mind regarding the clock rate of the processor? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so right now let's take a look and see what you guys think. So the most popular answer right now, wow, is C. We got 72% of you approve that. So can I have someone explaining why now you still think C is the right answer if you compare this question with the previous one, right? Previous question, we changed the serial to 0.4, and Now we change the carry look ahead adder to from 0.3 to 0.4 nanoseconds. Why that doesn't change the clock rate? Okay, I have Fox.
Because our clock rate, or strictly our clock rate, is dictated primarily by the length of the critical path, and we didn't change the timing of our critical path.
Right. So that's exactly the case, right? So so the thing is that, okay, so right now saying that you are hired by a company or no matter, so this is a concept you have to keep in mind, no matter you are designing a hardware or software. So saying that, okay, I like algorithm, I want to make my program faster, and I see a very complex algorithm in my program, I spend tons of time optimizing it. However, consider the whole component of your program. That's not a critical path. So saying that, well, so let's say like this is not a processor. This is a program that can perform shifter, that can perform adder, that can perform multiplier, and you are serving multiple clients concurrently, and all the clients, they must be synchronized in the meantime. And you are improving the process of one of the feature. However, because all the customer, we want them to receive the result at the same time. So it turns out that, well, even though you improve one of them, but if the one is not the one deciding the longest latency of those parallel operations, is not going to change the response time, responsiveness of your program. So the same thing here is that the processor, these are all components that we have, and our clock cycle time is depending on which of the component would go the slowest. So in this case, the clock cycle time is still 1 gigahertz. All right. So let's say I have this components, and assuming that 32-bit shift and add multiplier, we require 32 we require 32 cycles for the operation. So can you take a look and see, like, given the current clock cycle time, how many cycles do we need for the add? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so at this point, I see two popular answers. So both C and D, they are popular. So can I have some of you explaining what you think about? Okay, I have funds only. What do you think?
I picked C
Mm-hmm. Why?
because I see that we have a 8-bit CLA,
Mm-hmm.
so that we need four. I thought that was my logic. We need 4 times.
We
Uh,
need to do this thing 4 times, right?
yeah.
But why? Well, but seeing that, right, the carrier lookup that had adder only takes 0.4 nanoseconds. Why can I like, oh well, you know, and my clock rate is set to 1 gigahertz. Why is not 2? Why is not 8?
Aren't we deciding what the number of cycles?
Yeah, but your clock rate is set to 1 gigahertz, right? And
Uh-huh.
your latency is 0.4, right? Does that change your mind?
Oh, I'm not sure what you're looking for.
So right now, well, my clock rate is set to 1 gigahertz, right? Meaning that I have a total 1 nanosecond in a cycle, right? So the cycle time is 1 nanosecond, right? So and
Oh,
your adder, what do you think? Does that change your mind?
oh, so is it two cycles? Because in each cycle we can have 2
What do you
objects.
think? What do you think?
I think it's 2 now, but I'm not
You think
exactly
it's
sure.
2? You are not exactly sure? Okay. Okay, so hold on, Michael.
All right,
Wow.
I do not. This is a silly question, but in this case, we haven't specifically said that we're doing anything special to the clock. So
No.
this means that the serial 8-bit CLA is receiving the same clock signal as the 32-bit shift and add multiplier. The clock signal set to 1
So,
gigahertz. This does mean that we still need 4 clock cycles of the regular clock to actually
right.
do the math.
Right.
Now we
Okay.
could, if we wanted to, multiply the clock for that component to make it work faster. But we didn't say that we're doing that.
We didn't say that, and we are not doing that, right? And so, Fang Zong, actually, what you said originally is correct. So the 1 gigahertz here is just telling you we give your adder sufficient amount of time to accomplish its job. However, if we just feed the signal this small, right? Even though we have a huge amount of time within the clock cycle to do the rest of the stuff, maybe another add, but we can't because you still receive 1 clock signal, you still have 1 rising edge of the clock. Is that clear?
Yeah, so most of the
So
time.
I was actually, so you were right in the very beginning. I was trying to see if I can shake your mind and like give you some other thoughts to see if that would change your mind. But actually, you are right because it doesn't matter. It doesn't matter how long the clock signal is, right? If you
So
give it like
basically-
100 megahertz, you have to do. You can only do an add by 10 nanosecond, right?
Yeah, I just want to clarify. So most of the time we follow 1 cycle, 1 task, right? Is that what you're saying?
Well, I mean, think about that, right? Your register, right, is controlled by the clock signal. Your serial adder gets its input from the clock signal, right? If the clock signal is not changing, the register output is not changing, right? So in this way, even though I can receive 2 clock at the same time, I'm not changing my output.
Oh, okay.
Right.
That makes sense. Yeah.
Okay. All right. So thanks for your comment and thanks for being cooperative. Okay, Nicholas, question.
I'm sorry. Can you re-explain that? Because right now I thought I had it, then I lost it. So
Okay, so the whole circuit is controlled by the clock signal, right? The register only change its output on whenever receive the rising edge of the clock signal.
okay.
Right? And the register will feed its input to the serial adder, right? So if the input of the adder is not changing, the adder is not able to change its output and it's not able to, and even though, well, we did 2 carrier lookup ahead adding within the cycle, right? But the truth is that because the register is not receiving or updating its value until the next rising clock age, we are not able to accumulate that result as well, right? So everything is controlled by a clock signal. So no matter how slow the clock signal is, if we said this thing needs to be done in 4 cycles, it will be 4 cycles, as long as the clock signal is long enough for this job to accomplish. Is that clear now?
Yeah, I think so.
Okay, so for this we agree that we need 4 cycles for an add, and as I said, for the multiplication, we would need 32 cycles, right? So right now let's think about this is the high level state machine. We want to design a processor, and the processor has a shifter, has a serial adder, has an 8-bit serial adder, and then 32-bit serial multiplier, which only generate 1-bit result per cycle, right? So this is the high level stuff we have, and right now what we are thinking about is that, okay, if we want to put them all together, what do we need? So first of all, we have 2 numbers that we always want for as their input, and for the shifter, you probably want a second number to the number of bits that you want to shift. And for the adder, these 2 numbers are your inputs, and for the multiplier, these 2 numbers are also your inputs, right? And because we have 3 different units, so when we are updating our register file, we have to set which mux is giving us the final result, right? So that's the idea of our high level state machine, the whole design, right? So we want a mux. We have 3 different units, and however, how to set this mux input correctly, how to choose which to operate, right? Or say like for each of them, right? For the shifter, you only need 1 cycle to finish your job. For the adder, you need 4 cycles, and for the multiplier, you need 32 cycles, right? So if I have all this together, I need a controller to control what's going on right now for me to generate the output. So I want a controller. So you see this, right? It's similar to the case that we learned from the soda dispenser, is that you need a control path, you need a control unit to control your this components, right? The data path components. So for this, we probably need a few inputs. We need operation as well, like how many operations and are we done, in addition to the data path inputs, right? So this is what we have. And for the high level state machine, right, this is what we have. So let's say like I have a mux and I have 3 operations. So it will be 0, 1, 2. And for shift add multiplying, I would need 1 cycle, 4 cycle, and 32 cycles. So that's the high level idea, right? So and let's see, right? So and this is what we would imagine that we would be doing, is that so this is the high level idea of the high level state machine, and I just found there is one thing that I made a mistake. So what if we do this? Let's read this high level state machine, and can you guys identify a mistake, or say a few mistakes that I made? Right, look at this high level state machine. There is a mistake that I found that I made. At least one. Can you guys look at this one and raise your hand and tell me what you found? Fox, you are the hero. You found thing
I
wrong.
think I found it.
Okay.
So okay, so I'll follow it from init.
Okay.
So let's say we start at init and we want to add a number.
Mm-hmm.
I'm actually going to walk myself through this because I'm not 100% sure yet. We want to
Okay,
add
sure.
something. So we make our transition to the add begin. At this point, we are at clock cycle 1 of the operation at the add begin state. Remain is set to 3. Then our second state will be add in progress, in which remain will be set to 2. Then our third state will be add in progress, where remain is set to 1. Then our fourth state will be add in progress, where remain is set to 0. And then finally at state 5, add is done. But this was actually 5 cycles, not 4, where the shift is immediately done as soon as it starts in that one transition. That one transition is sufficient to process a 1 cycle shift, but for a 4 cycle add, we actually transitioned 5 times. And
Okay,
I think
so
that's the error.
So that would be one thing, right? So
And the multiply,
you mean
the multiply has the same problem because it's just the way
right.
it's counted.
So you mean if we want to fix this, the remain should be this, right?
Yeah.
Okay, one more thing. Okay, I have Alp. What do you think?
What I think is after each operation, we have option to go. For example, when we are done with multiplication, we have option to go to add or shift. What are we gonna do after we are done with shift?
Oh, yeah. Well, good point, right? So that's another thing which I forgot to draw here, right? So we should also have a MUL. We should also have an, oh, sorry. Okay, we should also have an MUL here. And I should also have an add here, right? Okay, that's a good one. What else?
Also, the empty arrows from begin to back to init. What they mean?
Say again.
The empty arrows from any begin for example,
Do we
multiplication
want it to
begin.
go back to init?
Yeah, what those mean? I kind of couldn't wrap my head around those.
So if you start, right, and it doesn't make sense to go back to init because if you go back to init, that you are delaying for another cycle, right? So, I mean, you can definitely do that, but it will give you an additional cycle, right? Okay. What else? What else? Okay, Nicholas, what do you think?
Does anything have to go back to the control unit?
Not really, right?
Okay.
Okay, so actually one more thing which I found this high-level state machine is not correct is that if you go back to our data path, right? One thing you will find is that we want the mux to update the register because you know some of the result register because like for the 8-bit serial adder, the 32-bit serial adder, we are not we are not aggregate. We have to aggregate the result for 4 different times or 32 different times. So it turns out that you need the mux to be set every time. You need the mux to be set in the beginning of your operation. So here, from the beginning, I have to set the mux to 1. And from the beginning, I have to start setting the mux to 2, right? So that's another modification we have to make because we want to aggregate our result into the register. And we share that result register, and we have to aggregate the result to the mux from the mux immediately. So that's another thing that we are missing here. Okay, so this is our great observation. And so right now I'm 100% convinced that you guys understand or figure out the concept of high-level state machine. So so I guess we are now finishing most of the high-level parts of the logic design. However, there are still quite a few details which I see the textbook is not covering well, but when I review the material from other schools, they do spend a lot of time talking about this. So that's why I want to expand some of the minor part things we still have another lecture and some time today to talk about this. So the first one that I want to talk about is the timing. So remember, this is the deep flip-flop. So the basic idea of deep flip-flop, and this is actually the most frequently used component in implementing our circuit. So what the deep flip-flop is doing is that we change the input before the clock age, and the output will respond to the change of your input when we receive the rising clock age, and keep the output for the whole cycle, right? So that's the operation of the deep flip-flop. However, when we draw this kind of graph, we always assume that we have perfect circuit, we have perfect clock generator, we have everything perfect. We think you have a well-behaved input that would raise the signal right before at the right time and hold it for long enough. However, that never happens. So we really need to let you know there are some timing constraints that we need to follow in designing the sequential logic. So we have talked about the sequential circuit is basically these two designs. However, even though the logic design seems correct, however, if your signal if we didn't fit the right signal, then the design could go wrong because the signal does not travel with 0 time. It takes time. So what are the delay that we have in a logic design? So there are 2 different types of delay. So the first, the 2 different definitions of the delay. So the minimum delay of a gate is called contamination delay. And usually we use TCD to represent that. And it's a minimum time from when an input start, when an input changes until the output start to change. So you can imagine this is the time we need. You will imagine that it's the minimum delay when the output will start to change. So say you have a circuit, and when I change my input, what's the smallest amount of time it would take for the circuit to start changing its output? However, this wording is very tricky. It says start to change, but the changed output is not necessarily your final output. So what's the delay we use for the final output? That's called propagation delay, TPD. So it's the maximum of time from the input change until the output is guaranteed to return its final value, stop changing. So if you receive an input and your output will need this amount of time to generate, that's called the final output would need at least this amount of time to generate. That's called propagation delay. So these are two types of delay. And through my verbal explanation, you probably don't quite get what's the difference of these two delays. So why don't you just look at this simple question and throw your answer to me really quick to see if you understand what's contamination delay. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so the answer is pretty interesting. So both B and C are very closely tied. So before I announce the answer, let me give you another question, this one, and tell me what do you guys think? Again, within 90 seconds. All right, 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after this time, I saw a majority of you pick A. So now I wanted to go back to the previous question, right? And let's do it again. And tell me, what do you think about this question now? Again, do it again. Okay, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so previously this question was a tie on A and B, but right now 61% of you think it's B, but still more than 30% of you insist it's A. So Nicholas, what do you think?
All right. So again, I don't know, but this is from what it looks like to me. Well, we know that contamination delay is once your input changes, you see when your output starts to change. So to me, I
Right.
thought the contamination delay was the blue path because as you go through each gate, your input's going to change and your output's going to be different. And maybe like
So
the
you're out.
slopes
So
too. So
you're
I
okay.
that's what I was thinking.
So look at this one, right? Where's the final output? Who gives you the final output? Who gives you the final output?
The last OR gate or the after the NOT gate, the third
The
gate.
last. Okay. So for this one, where its input comes from?
Its inputs coming from before that gate.
So one part of the input coming from the blue, the other part of the input coming from the red, right?
Right.
Which okay, so will the output change when the red input changes?
Yes.
Well, the output changes when the blue changes.
Yes.
Which one is happening faster?
The red one.
So when the output would, well, if right now we change both the input of blue and the red at the same time, which one would,
Oh, that
which
makes
would
sense.
make the output changes? Okay. So Fox, anything to add?
Oh, I see.
Fox?
Oh, I mean that was actually pretty much it. Yeah.
Okay.
Contamination delay is that. Yeah.
Okay, contamination delay means when the output starts changing, right? So once you have one input that changes its value, and the shortest one would start already change your output value, no matter it's correct or not. So in the opposite, the propagation delay means that when the output is going to be stabilized. So in this way, right, the output will be stabilized. Well, because we know the red is, once the red input is captured and it's not changing as long as we give it sufficient amount of time to hold this output, then it depends on when the blue signal will propagate to the final gate and generate your final output. So this is actually the time, once both of them adhere and plus the gate delay here, that's actually the final time that the output is not changing anymore. So the blue path would be the propagation delay of the circuit. So on the other hand, right, the longest the delay of the circuit is the propagation delay. The shortest delay of the circuit is the contamination delay. Okay, and by saying the delay is not about the length of the path, it's about how many gate delays, how long the wire delay in total that we have to suffer. Okay, so given that we know this, right, there are a few other constraints we have to follow when we are designing or deciding our clock cycle time. So you think the clock signal is like this. However, as you know that the clock signal is actually not rising immediately. It has a slope, right? So there is a period of time that we know the signal is not going to be stable and your circuit will start working here. So there would be a few time constraints on the clock cycle in a way that well, we have to follow. So those two constraints are setup time and the hold time. So the time before the clock age that the data must be stable. Remember, for the flip-flops, we capture the input. We capture the input of the flip-flops on the rising edge. So after the threshold value, the rising edge is already it's already considered the rising edge, and the flip-flops is getting this value right here and use this value to fit its rest of the circuit. So if you want the rest of the circuit to use that value for the rest of the computation, you must need your input to be stable for at least this period of time. So this is called setup time. So your time before the clock age that the data must be stable, meaning that your input time must be stable. And the hold time is the time after the clock age that your data must be stable. So, and the total amount of time plus this, it means that the total amount of time we require your data must be stable. So that's the constraint that we need to follow when we decide the clock cycle time. So we will talk about more on the clock cycle in the next week, and I will also update the preview slides because I think we don't have time in talking about some of the stuff which I think they are not minor. They are minor, and I don't think they are and some of them you probably learned it in assembly language. So we were probably just going to talk about them for 10 minutes, and then the next lecture would be we will continue the discussion on the cycle time, and we will talk about the future and very important things for the future logic design. So the next lecture will be very important, although a part of its content is not even in the textbook, but a very important thing of electrical engineering or computer engineering is to not follow the textbook, but giving you the most up-to-date information about what's going on right now. So before we finish the lecture, again, a few things that I want to let you know. So if you have done your IEval, or before you submit your IEval, make sure that you are ready to capture the screenshot submitted through iLearn. You will receive a full credit assignment. It's kind of like giving you a chance to drop your lowest graded assignment, another chance to bump up your grades. And also, we would like to receive your feedback and hopefully some encouragement to that the school know that both instructors and the TAs, they spend a lot of time in dealing with a lot of details and and a lot of fluctuations during the lecture, and also try to accommodate you guys by giving you free textbook and try to make up those missing materials in those free textbook, and we tried a lot of our effort to offer those online efforts. So hopefully you will appreciate it and reflect those on the iLearn. And the final exam will be on the exact time that the campus scheduled for us to avoid any of the potential conflicts. So make sure that you are free at that time. Okay, Fang Zong, question.
Hello.
Yes.
So I just wanted to ask you which part of our grade is going to be dropped. Again, I just wanted to ask you
The
to clarify
assignment.
that for me.
Assignment.
So I thought that you were going to drop the lowest lab or quiz or
No,
whatever.
well, okay. So by doing the IEval, we will drop an additional assignment. And
yeah.
we already
Okay.
dropped one. Lab, we already dropped one. Reading quiz, we dropped two. And for the attendance, as long as you answer more than 75% of the poll questions, you will receive full credits.
Okay. Can you make an announcement on iLearn? Because I looked around. I didn't find like a syllabus.
No, it's in a syllabus.
It is?
Yes,
Oh.
not in a slide of the first lecture, not on the
Oh,
web.
okay. I
Yeah,
see.
because it's kind of awkward to say that in a website, right? And
Okay, that's true.
but believe me, I don't think other sessions would do the same. They count every lab, right? But for me, I know you guys are busy toward the end, and actually, I think lab 5 and lab 6, they don't add up too much of your knowledge on logic design. So I'm okay for you to drop either. All right.
Okay, thank you very much.
Okay. If you don't have any question, I will meet you next time in the lecture, and hopefully some of you would go to our office hour.